Good morning all, I am B. Srinath. In this video, I am going to present about the RC circuits, especially the RC low pass and RC high pass circuits, and also we'll derive how it acts as an differentiator and integrator. Later, we'll derive the transfer function in the both the cases. Coming back to the RC low pass and RC high pass circuit, first of all, in both the cases, I will find out the explain about the RC low pass circuit diagram and RC high pass circuit diagram, and I will derive the equations using the KVL and also explain the basic principles and how it acts as an integrator and differentiator, and also at last I'll find out the transfer function using the Laplace transform. First is the RC low pass circuit. An RC low pass circuit is the sample passive network where it consists of a resistor and capacitor, where it allows only low pass frequency to pass through while attenuates or blocks high frequency signal. The reason is the capacitive reactance where Xc is equal to 1 by 2 pi Fc. We will derive or explain about the formula later. So based on that, it acts as the RC low pass circuit. Next is the RC high pass circuit, where an RC high pass circuit is another sample passive network where it consists of a resistor and capacitor. But here the output is taken across the resistor instead of capacitor, and also it can be derived as like it allows only high frequency signal while attenuates a low frequency signal. Coming back to the RC low pass circuit, as you can see the diagram, this is the RC low pass circuit. It consists of two elements, resistor and capacitor, where output is taken across the capacitor, and reactance of the capacitor is denoted as XC, where XC is equal to 1 by 2 pi Fc. So F is the frequency and C is the capacitor, and XC is the represent the opposition offered by the capacitor to the AC signals. So from the equation we can see at low frequencies the value of XC is very large, almost like an open circuit, so the output is obtained across the capacitor. At high frequencies the value of Xc is very small, almost like a short circuit, so the high frequency components are bypassed to ground and do not appear at the output. So by applying the KVL to the given circuit, let I be the current, so let I be the current flowing in that loop. By applying KVL to the loop, VI is equal to VR plus VC. Since the output is taken across the capacitor, as you can see, we can also write VC is equal to V0, so the total equation becomes VI is equal to VR plus V0. Here VR is equal to R is the resistor voltage and V0 is equal to VC is the capacitor or output voltage. And from the capacitor property we know that V0 is equal to 1 by C integral IDT, right? Differentiating on both sides we get I is equal to C into dV0 by dt. Substituting VR is equal to R, VR is equal to RC into dV0 by dt. So by solving this and later we'll dividing the RC, we get VI by RC is equal to dV0 by dt plus V0 by RC. See, the equation represents the relationship between the input voltage and the output voltage in the RC low pass circuit. As you can clearly see in the screen, dV0 by dt and V0 by RC are there. So the terminology with the dV0 by dt represents the transient or natural response, and V0 by RC represents the steady state or forced response. Now let's see how a RC low pass circuit acts as an integrator. We already know the basic equation of a low pass RC circuit. VA by RC is equal to 1 by RC into V0 plus dV0 by dt. You also know the terminologies of every term. So now let us assume the time constant is very large compared to the time period of the input signal. That means RC much greater than T, where T is the input signal time period. When the time constant is very large, the output voltage takes a long time to reach the steady state. This means the steady state 1 by RC V0 becomes very small and can be neglected. So the equation becomes VA by RC much approximately equal to dV0 by dt. So by rearranging dV0 is equal to 1 by RC VA by dt. So integrating on both sides, V0 is equal to 1 by RC integral VA by dt. We will get the final equation. That means this result clearly shows the output voltage is directly proportional to the integral of the input voltage VA. Now let us derive the transfer function of the RC low pass circuit. First you can see the circuit, and by applying KVL we get the VI is equal to VR plus VC, and since expressing in terms of current we will get VI is equal to IR plus 1 by C integral IDT, and output is taken across the capacitor. That means V0 is equal to VC is equal to 1 by C integral IDT, taking Laplace transform both sides, and we get V0 is of S is equal to 1 by CS I of S. So next, after defining the transfer function is the ratio of the output to the input. So T of S is equal to V0 of S by VA of S. After substituting, we will get the final equation for the RC low pass circuit. T of S is equal to 1 by RCS plus 1. Now coming back to the RC high pass circuit, as you can see the diagram where it consists of capacitor and resistor, where output is taken across the resistor. By applying Kirchhoff voltage law, let I be the current flowing through it. So we get the following equation: VA is equal to VR plus VC. Since the output is taken across the resistor, we can write VA is equal to V0 plus VC. And the capacitor voltage is given as VC is equal to 1 by C integral IDT. Resistor voltage VR is equal to R. Since VR is equal to V0, we can write VR is equal to V0. We can write IR is equal to V0. That is I is equal to V0 by R. And substituting I is equal to V0 by R. And after doing that all, we'll get dVi by dt is equal to 1 by RC V0 plus dV0 by dt, where dV0 by dt represents the transient response. 1 by RC into V naught represents the steady state response. Thus, this equation describes the fundamental relationship between the input and output of the RC hypercircuit. Now coming back to the transfer function of the RC hypercircuit, let us derive the transfer function of the RC hypercircuit. Starting with the KVL. By applying KVL, we get VA of t is equal to VC of t plus VR of t, and expressing capacitor and resistor voltage. Capacitor voltage VC of t is equal to 1 by C integral I of t dt. Resistor voltage VR of t is equal to I of t into R. Since the output is taken across the resistor, V naught of t is equal to VR of t is equal to I of t into R. Applying Laplace transform, V naught of S is equal to I of S into R will get, and input will get VA of S is equal to 1 by Cs into I of S plus R I of S, and after that we'll taking I of S common, we get VA of S is equal to I of S into R plus 1 by Cs. Transfer function is defined as the ratio of the output in the input, right? So transfer function we will get it finally R by R plus 1 by Cs. Coming back to the RC hypercircuit acts as a differentiator, now let's see how the RC hypercircuit can act as a differentiator. Starting the circuit equation from the RC hypercircuit equation, we know dVi by dt is equal to 1 by RC V naught plus dV naught by dt. This relates the input voltage VA and the output voltage V naught. And the condition for the differentiator, if the time constant of the circuit tau is equal to RC is very small compared to the time period of the input signal t, that is RC much less than t, then the capacitor charges and discharges almost instantly. This makes the transient term, that is dV naught by dt, very small, negligible, and the steady state term dominates. So under this condition, the equation becomes 1 by RC into V naught much approximately equal to dV by dt, or equivalently we can write V naught approximately equal to RC into dV by dt. So this means the output voltage V naught is directly proportional to the derivative of the input voltage VA with respect to the time. Hence the circuit is also called as RC differentiator. In other words, we can say the sharp changes in the input signal are emphasized at the output. Slowly varying inputs are suppressed. This is exactly why the RC hypercircuit acts as a differentiator.